Suppose you and a friend want to make a plan to play video games together. However, you live in the US and your friend lives all the way on the other side of the world in India. How are you going to make a plan to play video games? Luckily, you can call them with your cell phone and decide to communicate with them from there. Now, when you are talking over the phone, the sound of your voice is turned into electrical signals. For local calls, these signals often travel as radio waves to your friend's phone. However, for a long-distance call across the ocean, the signal is primarily carried by fiber optic cables as pulses of light. These signals, which are a form of electromagnetic wave, allow you to interact with your friend over long distances by carrying energy in the form of information described by sound and electrical signals. This is more or less how particles tend to interact when transferring energy and momentum between one another. But instead of imagining particles as a bunch of moving dots, physicists like to visualize them as ripples in spaces called fields. A field is kind of like a giant blanket that covers everything in the universe, and each kind of fundamental particle has its own field. So when we want to describe a particle in space, we describe it as a kind of deformation or excitation of the field. We can visualize this by pinching, scrunching up, or even folding the blanket to make different features and shapes that change the way the blanket looks and feels. This interpretation of particles comes in handy when we want to describe how fundamental forces, like electromagnetism, work in the subatomic world. Using our telephone analogy, when you pick up the phone to talk to your friend, a quick burst of energy, a message, is sent to your friend. The burst only exists long enough to transfer the energy it needs to. So while your friend didn't actually receive the message itself, they received the information you wanted to tell them through the message. In the language of fields, physicists call this message a virtual particle, a kind of temporary disturbance in the field that carries the energy or momentum to influence another particle. Although they aren't real particles in the sense that they can't be directly measured because they don't follow the normal energy-momentum laws, they do affect other particles, and those effects are what we describe as the fundamental forces in physics. For example, when an electron creates a disturbance in the electromagnetic field, it's represented by the emission of a virtual photon. Like a wave, the virtual photon carries momentum and energy to another charged particle that absorbs the virtual photon, transferring the information and changing the particle's direction and velocity. These interactions are often represented through simple drawings called Feynman diagrams, which help us see how multiple particles interact with one another or even create new particles. For example, the Higgs boson, an excitation of the unique Higgs field, is responsible for giving fundamental particles their mass. We often show the creation of the Higgs boson through a Feynman diagram involving particles called quarks and gluons, gluons acting like the glue that holds quarks together. In this process, two gluons are fused together, in which their interaction is mediated by a loop of virtual heavy quarks, specifically the top quark. On the other hand, when a Higgs boson decays, it can decay directly into a pair of force-carrying particles called bosons, or a pair of quarks. To sum things up, fields and virtual particles are invaluable when it comes to describing how particles communicate with each other through forces. Without a field to create an excitation that we call a particle, and a virtual particle to carry the energy to influence another particle, we cannot describe how particles are created or destroyed in our universe. On top of this, we wouldn't have a working understanding of where the fundamental forces in physics came from, leaving our model of the universe incomplete.